Hello everyone, and welcome back to the Kohi Game Engine series. Today we're going to talk about memory alignment. However, before we actually get into memory alignment and what that is and where we're going to use it and so forth, there is actually one thing that I want to go ahead and fix. So if we do a clean and a build of the engine in its current state and run, we actually have a memory leak currently. So right here in the game.c, I have code to say how many allocations we have per frame just by pressing M. And it keeps an allocation count, a running count. And if we go ahead and press that a few times, we're actually going to see that we have several allocations per frame and that this number keeps going up. So we do, in fact, have a memory leak that we need to address. Now, for the sake of brevity, I've gone ahead and researched where this actually is. We are going to be enhancing our memory system to track this a little bit better, but for now, we're just going to go ahead and fix the bug. So for right now, what we actually need to do is take a look at application.c, and within each individual frame, we are actually going through and let's see, we are in application run. So we have the render, we're performing all of this rotation and whatnot. And then we're going ahead and creating a render packet and going ahead and building a packet for each one of these views. And then we're going ahead and using that. So we're building a packet here, we're building a packet here, and we're building a packet here. However, we're not actually cleaning up the packet. So we actually have a to-do down here with a clean up the packet, and we're not actually doing that. So there are resources that are being allocated within these render packets when we build them that are not being freed. So if we actually go to this, we have our build packet. However, we don't actually have a definition for anything to be able to destroy the packet. So we have our on build packet here, but we don't have a way to actually destroy the packet once it's been destroyed. And not every type of packet is going to need this, but it's really something that we should go ahead and put in place. That way we have it when we go to actually, or when we actually do need it. So the first thing I think that we're going to do is probably go ahead and add the logic in to go ahead and be able to destroy that packet. So let me just take a look at my notes here. So we have in our render views, we have the definition already for the creation of a packet. So what we're going to do is in this interface, we're going to add a definition to allow us to destroy it. So right here we have on build packet, and now we have on destroy packet. So this takes a pointer to the view that is associated with it and a pointer to the packet to be destroyed. So that will provide us the interface for that. And now if we actually go to some of our views, we need to go ahead and implement this. So I'm going to do view. Let's go ahead and knock out the skybox one first. So we'll go to skybox, the H file for the skybox. And so all we're going to do here is just add our new definition for the, oops, let me put that here for destroy. So now we have a render view skybox on destroy packet. So I'm going to go ahead and grab this and go to the C file, and we'll go ahead and go to build packet, and we'll put this right below that. So we'll paste this here, and we'll go ahead and define that function here. And so this is where one of the actual arrays, or one of the actual resources is not being freed. So if we take a look when we're building the packet, we are actually let's see. Actually, this one actually is not. I was thinking of a different one. So this one actually does not actually need anything. So there's actually nothing to do here. So all we're going to do in this case is just zero out the packet. I guess you could argue that we don't really need to do that because it is a local variable, but for the sake of maintaining the interface, we're going to go ahead and do that on this one. So this one doesn't actually necessarily require it. However, if we go to the UI, so we want render view UI, and we'll go ahead and once again, we will just paste in a definition for destroy. So we'll put that right here. Again, it just takes a pointer to the view and to the packet. We'll go ahead and define this in the C file, right below, once again, our build. So right here. So we can see in the build that we are actually doing a D-array create here. And this is where we're creating an array for our geometry render data. So you could argue that doing this allocation every frame is probably not the best way to do it. There's probably a way that we should be caching this instead. However, that requires some other things to be in place. So for right now, I'm just going to go ahead and fix the leak. And so all we really need to do is, since we are just creating the array every frame here, we're going to come down here to our on destroy, and we're going to implement that to destroy the packet geometries, and then go ahead and zero the memory out for that packet. So that will fix the leak for that one. And then, as you might have guessed, the render view world, we're going to wind up doing the same thing. So we're going to go ahead and put in the on destroy right here, and we'll go ahead and take a copy of that. Render view world C, and we'll go ahead and put that in here. Let's see, that's render. So this is build here, I believe. Yeah. So we'll put it right here below build. We'll go ahead and do the same thing. So in this case, in our build, once again, we are right here doing a array create. So that is definitely going to be a memory leak there. So we'll go ahead and come down here and do the same thing where we destroy the packet geometries, D-array, and then go ahead and zero out the packet. And that will clean up that memory from use every frame for those packets. So along with that, we should probably go ahead and go into the render view system and hook up the function pointers. So all we'll need to do is open up the render view system, and I don't believe we're actually going to need to make any changes to the header file. This should all be contained within the C file itself. So here is where we are going ahead and creating or assigning the function pointers here. So all we're going to do is we are going to add for each one of these types a pointer to on destroy. So we have here for the world type, we're going to assign on destroy packet to render view world on destroy packet. And then likewise for the UI, we're going to do the same thing here. Just assigning that to the UI version of that. And then obviously for the Skybox version, we are going to assign the Skybox version of that. And that is actually all we're going to wind up doing. I'm not going to go ahead and we could, I guess, hook up something to build the packet or to destroy the packet the same way that we're building it, but we're actually going to have a pointer to the packet itself, so we can just call it against that packet, and we could just call the method directly. So that's what I'm going to do. So we'll go ahead and save that off, and then that takes care of the render view system. So now if we go into application.c, right here where we have the clean up the packet text, all we're going to do is go ahead and paste in a quick loop to just go through each one of the packets, point to the packet sub I, its view, and then say on destroy packet, pass through the view, pass through the packet itself. And that should solve our memory leak. So we'll go ahead and build that. We will run. Okay, and now when we press M, it looks like we actually still have some allocations happening. Did I not? Did I not hook that up correctly? Let me see. So that should be... We're still getting 7 every frame, which is bizarre. So let me debug this and see what's going on here. So our packet view count is 3. Let's go ahead and step in. Okay, so this one just zeroes that out, so that should be fine. Let's see. Oh, actually, I know what part of the problem is too. So this actually is destroying that. Then we zero. Okay, actually, yeah, I know part of what this problem is too. Okay, so the other part of this is we actually have fixed the leak, but there is a small bug in the memory, K-memory rather. K-memory.c with the actual reporting. And so what we're actually going to need to do is take a look at the free method, so the k-free method. So whenever we are allocating, we are increasing the allocation count, but we're not actually decreasing the allocation account when, or the allocation count when we're freeing. So that is just a minor bug, and so we will want to go ahead and probably do that right before this. Actually, we can do it right here. And so we're not actually decrementing this count, and so it's actually throwing our counts off. So if we go ahead and build this now and run, let me get rid of the breakpoint and pull the window back up. And now if I press M, it looks like we still are getting 1. So we'll have to come back and figure out what that last one is. If I had to guess, there's probably one more that we're missing somewhere. So let's see. Let's take a look at the... So the skybox doesn't have anything that needs to be freed. Let's see. The render view UI build packet is just creating this one. And then I suspect it's actually the world packet that's actually an issue. In fact, I think I know where the issue is. So, yeah, okay. So, actually, we do still have a leak here. So, our render view world on build packet, we are actually creating 2 D-arrays here. So, we're actually creating one for geometries, which we are cleaning up now. But we're also creating one for geometry distances, and this is what's used to sort the geometry. So the geometry distances is purely used just for the quick sort. So actually what we can do is down here before we return true, we should be able to do darray destroy, and we'll say geometry distances. Because we don't actually save that beyond the packet creation. So that should actually take care of our last memory leak. So we'll go ahead and run again. And now, if I press M repeatedly, we're sitting here at 118 allocations. We're not allocating extra things per frame. So we've actually resolved our memory leaks. So great. That is all that we need to do for that. So now that we have that out of the way, we can go ahead and get into the meat and potatoes of the changes that we're going to be making for memory allocation. Now, or I should say memory alignment rather. So what are we talking about when we say memory alignment? What does that actually mean? Well, it means a couple of things, but for our purposes right now, we're talking about memory address alignment. So if we took a look at, I'll just set a breakpoint. Maybe let me go to the application, application.c, and I'll go into, let's see, we'll go to application run should be good enough. So we set a breakpoint, we run. All right, so each variable that we create actually has an address in memory. So you can see that here. And we've talked a little bit about memory addresses and things of that nature before. But what we haven't talked about is what some APIs require in terms of what that address actually is. So there are several APIs out there that require the address in memory to have a certain alignment in bytes. And what that basically means is that this address needs to be aligned to a specific power of 2. And what that specific power of 2 can vary from API to API, and sometimes can vary within that API. So a couple of examples of this are going to be SIMD. So when we start actually implementing SIMD in our library for our math library, that is going to require this as well. That's single instruction, multiple data, and we're going to go into that in a separate video. So that requires it. Vulkan also requires it. Specifically, if you're going to be using your own custom allocator, which is the next thing that we're going to be doing in the next video, that requires specific memory alignment as well. So we might have to align the memory address to maybe an 8-bit or 8-byte address or 16 bytes or what have you. And so all of those various alignment requirements require us to make some changes in code to ensure that that address is aligned to a specific power of 2. So this number that you see here is the address of the variable. That is what we actually need to align. And so there are various performance benefits and drawbacks to doing this depending on the platform. PC, generally speaking, is pretty flexible with this, but a lot of consoles are actually super picky about memory alignment. So memory alignment is definitely an important thing to bear in mind, and we're going to implement the first phase of that now, which is address alignment. There also is alignment in terms of individual elements within a structure that we need to discuss, and things to consider such as padding and whatnot. We've touched on a little bit of that beforehand, but for all intents and purposes right now, we're purely talking address alignment. And there also are other considerations in terms of cache when it comes to alignment, but we're not going to get into that right now. We are going to cover that, just not right now. So all of what we're going to do here is we're going to support address alignment, which will allow us to write our own Vulkan allocator, which eventually will wind up allowing us to have a little bit better understanding of how Vulkan is actually requesting memory and have a little bit more control over some of the aspects of that, like telemetry, which we're eventually going to add in. Anyway, with all that out of the way, let's go ahead and start implementing our memory alignment. So the very first place that we need to align is going to technically be our dynamic allocator, because our dynamic allocator is what powers our platform or our memory alignment, our memory allocation, sorry, and freeze, right? So we're calling our dynamic allocator that we're using within this, and that's what is responsible for pulling out of that huge memory pool that we have. And so our dynamic allocator is going to be the place that we need to implement some of the logic, but our dynamic allocator actually relies on a free list. And the free list does not know anything right now about alignment. So our free list is actually going to be the first place that we need to modify to support all of these changes. So that is where we're going to start, is by putting our allocation routines, our aligned allocation routines in our free lists. So right now we have a free list allocate block, which performs an unaligned allocation of memory. So it basically just picks the first free space that has enough space in it within our memory block and hands it back. And that's all it does, which is fine for a lot of things, but for anything that requires an aligned allocation, it's not so great. And so what we're going to wind up doing is adding a new method that says free list allocate block aligned. And it's going to take a pointer to the list as we have before, size as we have before, and now we're going to provide an alignment. And this alignment is going to be the number of bytes to align to, typically a power of 2. And then we also have the out offset, just like before, and this is going to be the final offset. And then we also have an alignment offset. And that is so anything calling this understands how many bytes we had to shift the allocation to basically align or to get that aligned addressed. Now, what do I mean by shift? So let's say, for example, we have, whoops, don't want to comment here, I just want to block. Okay, so let's say that we have a couple of blocks of memory here. So we have, I don't know, we'll use simple numbers. So we'll say block 1, block 2. Actually, let me make this 0-based. 3, right? And we'll also say we have 4, 5, 6. Let's go all the way to 7, okay? So we have these individual one byte blocks of memory that we can allocate from. And let's say that these first 2 bytes are already allocated, right? So these are previously allocated, right? So our free list pointer is actually here. But let's say, for example, that we need an allocation that is aligned to 4 bytes, right? And we need our address to be aligned to 4 bytes. And so instead of being able to return 2 at this point, because that is not aligned to 4 bytes, we actually need to align that to, you know what, I actually shouldn't make this 0-based. This should be 1-based. That's my bad. That's going to be confusing, so sorry about that. Yeah, we'll go 8. Okay, so we'll say that these first 2 bytes are allocated, and then our pointer is right here for the next allocation. But we're saying we want an allocation aligned to 4 bytes. So what we really want is we want this address here. And so what we need to do is we need to actually offset by a byte to get this address. So we actually want this address, right? And if the previously allocated pointer was here, right, we'd have to offset that by 2 bytes to get here, right? So this is our target address that we want, and then this is what's already been allocated. I hope this is at least somewhat clear. So what we need is we need a function in place to say, okay, well, where is the pointer currently at, and what alignment do we need, and then perform some logic there to get us the next aligned address. And so to further this example, let's say that there was also an allocation that started, let's get rid of this. We'll say that there was an allocation that started here and maybe ended here, right? and then maybe there was another one here, right? There was another one here, there was another one here, right? So these are all just different blocks of memory, right? So what we're, actually, let me get rid of this one. So what we would do is we would say, okay, well, 4 is already taken, so we'd go to 8, right? And so all of this to say, we need something that is going to tell us what the closest address that is also large enough to provide that aligned address to us, what that is, and how many bytes we actually had to offset to get that address. Because when we free, we're going to need to know that. And basically what we're going to do is we're going to have padding at the front, and then we're going to provide the actual block of memory. So our padding is always going to be at the front to provide that offset, that alignment offset, and then after that we are going to go ahead and provide the aligned address. So technically this does use a little bit more memory, but you know, because it's a requirement, sometimes we may not have a choice. So that being said, an alignment of 1 is basically the same as just calling this guy. So what we're going to do is we're going to change our free list allocate block to call our allocate block aligned with an alignment of 1. And that's essentially going to keep anything that was originally calling this from breaking, while also hooking into our new alignment code. So I hope all of that makes sense. If it doesn't, I can always make another video to clarify or try to clarify in the comments. So what I'm going to do is go below free list allocate block, and I'm just going to paste in our definition here for our block aligned. And I'm going to grab everything that is within this definition and cut it out of allocate block and put it in allocate block aligned. Then I'm going to come back up here and to our method here, I'm going to call, let's see, we're going to need a pointer to the alignment offset, which in this case we don't actually care. So I'm going to create a U16 rubbish alignment offset. We'll go ahead and set that to 0, and then we will return free list allocate block aligned. And to that, we are going to pass list size. Alignment is going to be 1, because an alignment of 1 is basically saying we don't care about the alignment. And then the out offset, we're just going to pass through. So we have out offset, and then the alignment offset is going to be the address of rubbish alignment offset, because we're not bothering to alignment. We don't actually care about what that alignment is. So anything that actually calls this is going to know that we don't actually have an alignment to keep track of, so we don't actually need to return that out. Okay, so before we actually make our changes here, I do want to go back to free list H, and I want to make one more change, because we have an allocate aligned. We also are going to need a free aligned. So we have our allocate block aligned. If we come down here, we have our free block here. We're going to add a free list free block aligned as well. And this is pretty much identical to our free block. It's just adding the alignment offset. So the way that this API works is you make a call to allocate block aligned, which gives you the out alignment offset that you then pass here to the free block aligned when you're ready to free the allocation. Now our dynamic allocator is going to keep track of these things, so we don't actually have to track it outside of this. Again, the free list is sort of something that's really only internally used anyways, so anything that is using this needs to be smart enough to know how to hold that alignment offset so that it can go ahead and provide that when it's done. Okay, so we have that. And now we're going to come back into the free list C, and we're going to go ahead and implement our changes here. So we've gone ahead and forwarded this to our alignment with an offset of 1. So now we're going to make our changes to this function to ensure that it works as we need. So the very first thing that we need to do is we need to get an aligned offset for the particular node that we're going to be looking at. So within our while loop, in other words, while we're looking at the nodes, we are going to obtain an aligned offset. And this is going to use our getAligned function that we put in defines h to get an aligned number based off of the operand that's passed in and the granularity. So that is basically just going to take that number and align it to whatever number we pass in. In this case, it's going to be a power of 2. And that alignment is going to, or that, I should say the granularity is just our alignment that's passed into the method. So we take the offset of that node and we go ahead and obtain an aligned offset from that, which basically tells us what the address is going to be, or how much we actually have to offset that. So we get that offset by taking the aligned offset we obtained here and subtracting it, or subtracting from that the node offset. And then we're going to go ahead and use both of those pieces of information to say how big is the actual size required by the allocation. So that is going to be the size plus the alignment offset. So if we pass 1 here, then our alignment offset is actually going to be 0 because it's already considered aligned. And so this aligned size would be 1. If this is 2 and it's then depending on where the node's address is, it may be size plus 1 or size plus 0, and so on. And so we're going to go ahead and calculate those 3 pieces of information that we need to know there. And then we'll come in here and our if check actually needs to be slightly changed. So right now we're saying if node size equals size. We can't just use size anymore. We actually need to use aligned size because that is a little bit bigger. So it needs to be able to handle the size of the allocation plus any padding that's required. And then we'll go ahead and check to also say, is the alignment offset 0? And this is also basically, instead of an exact match, this has to be an exact match if it's also aligned properly. If it's not aligned, it won't be large enough. So we'll go ahead and set that. So instead of using the nodes offset, we're now going to use the aligned offset. And then from there, we actually are going to need to set the out alignment offset to 0, right? Because in this case, we know that that the node is already aligned as is, and it'll be just fine. So this is to ensure that. And then otherwise, if our node size is larger than not just the size but the aligned size, then that means it's big enough to hold it, but we have a little bit of extra space there. So now instead of just saying that the node is larger, deduct the memory from it and move the offset by that amount has to change. So we're going to say it's the requirement plus the alignment offset, and then we'll deduct that full amount and offset it by that amount. So that means that our offset needs to not just be node offset, but it needs to be aligned offset. And our out alignment offset now needs to be set to, alignment offset. All right. So, I believe we also need to change this from size to aligned size. Line size. So, that should be right, align size. Yeah, that's fine. Okay. So now we should be good to go. Let me just double check that I used offsets. Okay. So that should handle our allocations for us and just make sure that they're aligned properly. So the next thing that we're going to do is we'll go ahead and implement the free aligned method. So I'm going to go ahead again and just copy this here. And right below free block, we're going to paste in our definition. and come back up here. Did I get rid of the, yeah, okay. So we'll come back up here to free list, free block, and I'm gonna grab all this logic, just like we did before. Cut it out of there and paste it in the free block aligned. And all we're gonna do is forward this to say return free list, free block aligned. We're gonna pass it the list, the size, the offset, and a alignment offset of 0, right? Because if we're calling this, we would not have had a alignment offset at all, right? So we're calling this against anything that was unaligned. So now in our free list free block aligned, we are going to go ahead and modify this to give us the information that we actually need, or to go ahead and calculate the information that we need to free the node properly. So before we go ahead and check the given nodes, we need to get the unaligned offset, which is the offset that's provided minus the alignment offset. So it just moves it back to before that padding in memory. And we'll go ahead and calculate the unaligned size, which is going to be the size plus the padding of the alignment offset. And that means that down here within our checks, all we're going to have to do is change this from offset to unaligned offset, and from size to unaligned size. And we'll have to come down here to our while loop while we are checking each individual one. And instead of checking against the node offset against the offset, we're going to check that against the unaligned offset. And instead of adding the size back, we're going to add the unaligned size. Okay. And let's see. So this one covers the case of a completely new node. So we actually need to modify this as well. So instead of checking the node offset against just offset, that needs to be unaligned offset. And we need to change the node offset and size back to unaligned offset and unaligned size. And I believe that is actually all we need to do in here. Okay. So I believe that's actually all we have to do in this entire file as it is. So that is all the modifications to free list. So the next thing that we need to do is we need to actually go into the dynamic allocator and modify that to point to our new methods. So all of the changes for the dynamic allocator are going to be pretty much mirrors of what we've done within the free list. So what we're going to do here is we have our dynamic allocator, let's see, allocate right here. And so just like we did before with the free list, we are going to have a aligned version of this allocate. So all this is going to do is take the allocator, the size, and then the alignment that we need. And that's pretty much just going to be a pass-through. And then we also are going to do the same for free. So our free is actually going to work a little bit different. So our free in this case is actually going to be smart enough to know how big the block is, because we're actually going to add some information in here to tell us what the size of that block is. So we actually don't need to provide the size for this one. It's actually going to know that internally. We may actually be able to adjust this to no longer take size with these changes as well. So for right now, I'm going to leave this as is and just sort of pass it through. But yeah, we're going to have to eventually go in and modify this one as well. So we have those. We also are going to be adding one more sort of utility method, and this is going to obtain the size and alignment of a given block of memory. So this can fail if an invalid set of data is passed. And so basically what this is going to do is say, for this block of memory, what is the size and what is the alignment of it? And that is going to give us a utility to be able to manage that manually if we need to. Okay, and that's also going to provide us a little bit more information in terms of telemetry eventually when we start hooking some of that stuff up. So that is actually it for the H file. And now we will go into the C file, which is where the meat and potatoes are of this change. So we'll go to dynamic allocator C. And we're actually going to add a new structure to keep track of our allocations for us. And of course, this does mean that our allocations are now going to have the overhead of a structure that holds the data, but it's also going to mean that we have a little bit of a smarter allocation system, and it's going to be a little bit easier to debug. So I'm willing to make that change because these days there's usually plenty of memory, and this is not going to wind up taking huge amounts of memory, especially if we're smart about our allocations. So we are going to be creating a header for each allocation. We're going to store the size, the alignment, and the alignment offset of each of those allocations. And this is what's going to provide us that utility to go ahead and be smart about our allocations in Freeze. So the first thing that we're going to do is we're going to go back to our header file, which is here. Let's go ahead and get our allocate aligned. We'll go ahead and fill this out first. So I'll go to right after our allocate and paste that in so that we can define that there. And I'm going to take, just like we did in the free list, all this logic out of here and move it down to our aligned method. And then in our original method, we're just going to return dynamic allocator allocate aligned. And we'll go ahead and pass through the allocator. Whoops, allocator. We'll pass through the size, and we'll pass an alignment of 1. And now that makes things, everything go through this allocate aligned function. So the next thing that we're going to want to check is to make sure that we have an allocator and a size provided, and we also want to make sure that an alignment is passed, because if you pass 0 for the alignment, that's not really a valid thing, and we need to smack the user for that. So again, this is not something that's really going to be used in the public areas of the engine most likely, but there's the possibility that exists. So the first thing that we're going to do is actually modify our error message at the bottom. So if it fails this, we're going to change this to say it requires a valid allocator, size, and alignment. And let's see, we also have a rename here, so I'm going to replace that error message there. And we're going to, first off, we're going to get the actual size of the allocation. So right after we set our offset to 0, we're going to account for some space for the header. So our actual size of the allocation is now going to be the size plus the size of the header. And we're also going to start off with a alignment offset of 0. The next thing that we're going to do is we are going to take this definition of block, this void pointer for block right here, and we're actually going to move it out here and start it off with being defined as 0. So we are also going to remove this return statement here and just set block. So now we can say our free list allocate block, which actually needs to be converted to the aligned version of that. And that takes the list, the size, the alignment, and offset. So we're just going to pass through the alignment. And we're also going to pass through the alignment offset so that we get that back here. All right, and actually, let's see. Oh yeah, we need the offset as well, so the address of offset. Okay, so now we will pass through our alignment. We will get our offset back. We'll also get the alignment offset to save to the header, and we will go ahead and allocate that memory. Next, we will actually need to create our header. So for this, I'm just going to paste in some code here because it's a lot quicker to do that. So we're going to set the header info. So we're going to create a alloc header just by cold casting our memory block plus our offset, and then casting that to a alloc header pointer. Within that pointer, we will set the alignment, we will set the alignment offset, and we will set the size. So this should be the right. So this will be the size of the requested allocation, not the size plus the alignment or the header size. That all will be known by parsing this header and obtaining that information from there. Next, of course, the block is just obtained the same as it was before. It's just instead of using just the memory block plus the offset, we're also offsetting it by the size of the header, so that way we allow room for this information that we just set to not be clobbered. Let's see. Okay, so next we need to make a small change here. So instead of returning 0, we're just going to set block equals 0. And technically this is redundant because we already did that up here, but I just want to be explicit about it. If we do have an error here, I want to be explicit about exactly what happened there. And then once we're done with that, we will return the block here. So it just makes the code a little bit cleaner to understand the flow. Okay, so that is it in terms of the allocate aligned. Not a whole lot of changes there, not complicated either. So the next thing that we're going to do is we need to do the same for our allocator free. So we'll come down here and grab a copy of this signature for the free aligned. And again, we're going to move this logic to the free aligned. And our allocator free is simply going to return dynamic allocator free aligned. And we're going to pass through allocator and just the block. So you can actually see the size here is no longer actually used or required. I probably am going to go through and make changes to that eventually so that we don't have to pass along the size anytime we do this. But for right now, I'm not going to worry about it. Okay. So within the free aligned, we obviously no longer have the size here, so we shouldn't be trying to check that because it doesn't exist. So we have here the K error needs to be updated to say free aligned. Same thing with these error messages here. And then I believe actually the only changes that we need to make are actually within this section here. So all of this here is just checking to make sure that we're not outside the range, which none of that should really change. So what we're going to do is we're going to first obtain the header and then get the actual size of the allocation. So we'll do that right before our call to free the block. So again, we get the header by just cold casting the block, and then we're going to offset that block by the size of the allocation header. So we're going to move the pointer backwards by that much, and that'll give us our pointer to our header. Of course, we cold cast that and we get the type. Our actual size is going to be the header size, which is the size of the actual allocation itself, plus the size of the header itself. And then we'll go ahead and call free list free block aligned. And this, of course, takes the list. It's going to take the size. So instead of that size, we're going to pass through actual size. It then requires the offset, which is not just going to be the offset by itself, but it's going to be the offset minus size of alloc header. And then, whoops, it's also going to require the alignment offset. So that's going to be the header alignment. Actually, that should be alignment offset, not alignment. Okay. So I think that is all we need to change in that method. So that looks pretty good. So the last thing that we need to do is implement this dynamic allocator get size alignment. So I'm going to go ahead and grab a copy of that. And all we really have to do here is we're going to do the same thing that we essentially did here, where we're going to go ahead and get the header from the block. And we're going to set the value and the out size and out alignment pointers to whatever is in that header. And that is all it really does. And then, of course, we return true. We probably don't need this to be a Boolean, but I did that just in case for some reason we want to add some error checking to this. Maybe do some sanity checking on these values in a debug version or something like that. So I went ahead and stubbed that out, but we're not going to wind up using that right away. Okay, so that is all of the changes to the dynamic allocator. So I think the next change I want to make is going to be within K-memory itself, because that is where a lot of our code actually calls into. So we'll go to kmemory.h, and we're actually going to stub out some changes that are also going to be needed for the next section of this. So right now we have all these memory tags. We're going to add a few more, and this will give you guys a little bit of a preview as to what some of the next changes are. So we are adding a tag for Vulkan so that we can track our Vulkan allocations. We are also going to track something called external Vulkan allocations, which is for reporting purposes only. It's allocations that maybe the driver makes that we don't actually have control over. And so we want a separate way to report that. And I'll jump into that a little bit more once we actually get into our Vulkan allocator. We're also going to set something up for Direct3D and OpenGL, because eventually we're probably also going to want to keep track of those allocations as well. And then we're also going to have a tag for GPU VRAM allocations. So this is not specific to Vulkan itself, like a Vulkan specific allocation, but maybe an allocation within that, say like a buffer or something. And so that is what that is going to be used for. So we can get a little bit more granular with our allocation reporting. So as we have done with the free list and the dynamic allocator, we have our k-allocate, and now we are going to have a k-allocate aligned, which of course is just a size, alignment, and a memory tag. So all we're doing right there is just adding that alignment in there. And then we actually want to do a k-allocate report. And this is just a report allocation that we have no control over, that's made by, say, the GPU. So this external allocation right here would be an example of that. So if we want to report an allocation that we were notified about but have no control over, and it's not actually within our memory banks, this is how we will go ahead and report that. Again, we're going to need that for the Vulkan allocator. So we have an allocate aligned. That means we need a k-free aligned. And so that is basically just going to take the block, size, alignment, and tag. And again, I'm probably going to wind up at some point maybe getting rid of that size, but for right now, we're going to keep it in place. Since we have a k-allocate report, we also need a k-free report. So this is, again, just reporting those external frees for allocations that were made outside of our application, say by the graphics card driver. And then we also are going to expose a get size alignment. So this is from our dynamic allocator. We're basically just exposing that on up to our memory system so that we don't have to call the dynamic allocator explicitly, because we actually can't do that. It's not exposed. So we need a global way to say, okay, for this block of memory, what is the size and alignment of it? And again, we're going to need that for the custom Vulkan allocator. So those are the things that we're going to be adding. And so now let's go ahead and we'll go ahead and fill these things out. So the first thing we're going to want to do is go to kmemory.c, go all the way to the top, and we're going to need to add to our memory tag strings. So right here we have our resource. We're going to add to that our Vulkan extension, Direct3D, OpenGL, and GPU local. So those things, of course, line up with the changes that we made all the way up here. So just so that we have string representations of those things. So we've got that. We'll also need to come in here and grab a copy of kallocate aligned so that we can define that. So right here, after we have our kallocate, we'll go ahead and put our kallocate aligned. And as we have done before, we are going to take the logic out of the allocate, put it into the aligned, and tell the allocate to call the allocate aligned. So we'll turn kallocate aligned, and we'll pass through the size. The alignment is going to be 1, and then the tag. Okay, and that'll just return that. And now we are always passing through our aligned function. Since we've updated that, we actually have a couple of messages in here that are referring to kallocate. We're going to change those to kallocate aligned. So just go ahead and do that for consistency purposes. And then the only change that we should really need to make is right here where we are allocating from our dynamic allocator. We need to change that to use the aligned version. So we have our allocator, our size, and now we just pass through alignment. And that's all we should have to do for aligned. So the free is going to be the same thing. So we'll come down here and we will go ahead and grab the k-free aligned. And come down here and paste that so we can define it. Grab everything out of k-free. Put it in k-free aligned, and then we'll call k-free aligned, passing the block, the size, the alignment is going to be 1, and then the tag. All right, and that just will work as is, so it pipes everything through this. Our k-free aligned, we'll need to update our warnings and our errors, which actually I think that's the only one. And from there, I think that's actually all we really need to do, except we need aligned here. So right here, we just change that to use the aligned version, which just requires us to remove the size. Okay, so the next thing that we'll go ahead and do is, and I know we're jumping around a little bit, is we're going to handle our kallocate report. So we'll implement that right here. And all this is going to do is just update our reporting. So essentially it's going to be this section, like a copy of that section. So basically we just obtain a mutex lock on our allocation mutex. We change our total allocated to add the size. Our tagged allocations, we go ahead and add the size to that, increment our allocation count, and then perform the mutex unlock. And then our k-free report is basically just going to undo that. So I'll go ahead and grab this definition here. And come down here right before 0 memory. And again, this is going to just take a mutex lock, update the total allocated, the tagged allocations for the specific tag, decrement the allocation amount, or the allocation count rather, and then release the mutex lock. And then the last thing that we need to do is this k-memory get size alignment. So we'll go ahead and copy that over here, and we will implement that right here. And all this is going to do is call dynamic allocator get size alignment, and we're just going to pass through block out size and out alignment. All right, so that's literally just a pass through, and we need to return that. Okay, and that is actually everything that we need to do for our k-memory. So, and actually, I believe that is everything that we want to do in general. There is one more change that I want to make to game.c. So right now, our game is basically whenever we press M, we're just spitting out the number of total allocations. But I actually want to report on the usage, because we're actually going to want to start monitoring that as of the next video. So to do that, we need a character pointer. Whoops, character pointer. We're going to call this usage, and we're going to set that to get memory usage string. And if you recall in the comments, right here, this memory should be freed by the caller, right? So we'll have a memory leak if we don't take care of that. So the first thing we're going to do is call kinfo, and we're just going to print that usage to the console, and then we're going to call our kfree, and this is an unaligned allocation. So we're going to say usage, which is the block of memory. The size is going to be string. Oops, we don't have string, so we'll need to include core kstring.h. So we need the string length of usage, and then we'll want +1 to include the null terminator, and then mem tag string. Right, and we're using memory tag string because in get memory usage string, when we actually perform the allocation, we are using string duplicate, which uses the memory tag string. So we probably ought to have like a string destroy that does that for us. In fact, do we not have that? You know what? I'm going to implement that too, because that's kind of annoying. So yeah, let's go ahead and do that. So I'm going to go to kstring.h, and we have string duplicate. I'm going to put that I don't think I want to go all the way to the bottom with it. Let's put it right underneath this. I guess that's fine. So that's going to return a void string. I'm going to call it string free. We're going to take a character pointer string, and we're just going to free that. Okay, so freeze the memory of the given string. The string to be freed, and it doesn't return anything. Okay. So we'll go back to kstring.c and string duplicate, put it right here. And we'll go ahead and take what we're going to put in game.c and use that, this line right here. So we'll say if string, right? Because if string is obviously a null pointer, that's no good. And then we should probably also check the length of it as well. So, well, actually, even if its length is 0, it's still going to have a length of 1 for the null terminator. Yeah, so this is fine. I don't think we need to check that. Because even if it's an empty string, you're still going to have memory to be freed. So we'll go with that for now. This is not going to be perfect, obviously. It will leak memory if you change or null terminate the string at any point. So we should probably put that in here. Note, relies on length of string. Will fail if null terminator is moved. Although I suppose we could get the size alignment. You know what? That's actually probably a better way to do it. Instead of using a string length, let's do k-memory get size alignment. And we'll say u64 size equals 0. U16 alignment equals 0. And we'll pass through the string, the address of size, and the address of alignment. Double check that result in case that fails for some reason. And then instead of using string length here, we will go ahead and use size. And since we're actually using k-free and we have the alignment, we might as well go ahead and use the aligned version of that, which is going to take the size, then the alignment. Since we have it, might as well use it. And that should cover us. Technically speaking, if this fails for some reason, it's going to silently fail. So we should probably put oh, we don't have the logger in here. You know what? To do report failure question mark, because I don't think this actually can return false. No, so it only returns true for right now. So I'm just going to leave that as a to-do, and then I'll put one here to-do as well. To-do report null pointer. Anyway, now I can go to game.c and get rid of this and just say k-string, or was it string free? String destroy. No, string free. Yeah, string free usage. And that should free up the memory for that so that we don't leak. Right, okay. Let's clean and rebuild. What did I miss? Unused variable actual size. Dynamic allocator. Actual size. So allocate aligned. Oh, okay. This should be actual size. And requested size, yeah, okay. It's actually a good thing I have that turned on, because that would have been kind of a nasty bug. Okay, so that should be using the actual size, so let's go ahead and run. Yeah, it looks like we're good. Let's print out some memory usage here. So we can see all of our tags seem to be reporting correctly. Okay, let's go ahead and let's just write this out a couple more times. So we still are, what, 118, we don't have any leaks, so that's good. I'm gonna go ahead and load the entire scene. And let's see, so it looks like we're still rendering just fine. And now it looks like we have at least a little bit more memory used. Now, you'll notice that we're not tracking a lot of these allocations. So there's actually a lot of video memory being used right now, but we're not actually tracking it. And that is because we don't actually have the Vulkan Allocator hooked up yet. So that is going to be the next thing that we are going to do, is we are going to hook up the Vulkan Allocator. But that is going to be for a separate video, because this video has gone on long enough. So I'm going to go ahead and call this video right here, and I will see you guys next time. Thank you guys so much for watching. I appreciate it. If you haven't already, go ahead and hit the like button. That always helps me out. Leave a comment below if you have any questions or just want to give me some feedback. And then if you haven't already, consider subscribing and hit the little bell icon there so that you get notifications as to when new videos in this or other series drops. And I will see you guys next time.